Hope you're all very refreshed, so we can keep getting into moving forward via a lot of interesting models. I was just wanting to add a few things to the latent transition model here on slide 33. And some questions came up in the break. One is, do you really have to repeat all of these items at both time points? For instance, what if U14 is not repeated, but you don't have it at time point 2, or you have another one at time point 2? Well, you have the flexibility that you have in, say, confirmatory factor analysis over different time points, or in item response theory over different time points. You may think that you have the same construct. You can argue that you have the same construct if at least a majority of the items are the same across time point, and it's relevant for them to have measurement invariance across time point, so that it's a plausible statement to say that you're measuring the same construct at the two different time points. So you don't have to have all of the items the same. And Linda alluded to the fact that you don't have to have, irrespective of that, say that you have all the items the same, you don't have to have the same number of classes at the different time points. But then, of course, the transition modeling or the interpretation of the transitions become more complex. You could, for instance, have 2 classes at time 1 and then spreading out into 3 classes at time 2. That could have some interesting natural interpretations. But it no longer will be movement among the same classes across the time points. But that's not an essential requirement to have movement among the same classes. You can have, in this kind of analysis, you can have different number of classes, and in fact, you don't even have to have the same items at all at the different time points. This could have to do with externalizing behavior, and this could have to do, at an early time point, that this could have to do with, so this is acting out antisocial behavior, and this could be drug behavior. And you're not interested in transitioning among the same classes, you're just interested in seeing how class membership at time 1 for antisocial behavior influences different kinds of drug use classes at the later time point. So you have quite a lot of freedom here that we didn't cover. Now, if you want to read more about the more conventional latent transition analysis, on slide 45, you have a group from Pennsylvania State University, Penn State. Stephanie Lanza, I think, is a student of Linda Collins, who's been contributing to latent transition analysis. And also have this article applying latent transition analysis to alcohol and substance use research. And here is a paper by a former student of mine in developmental psychology, an overview of Markov chain methods for the study of staged sequential developmental processes, where you impose a common restriction is that the classes correspond to a progression of understanding very little to understanding very much. And the idea is that you don't go backwards in your transitions. You only become more informed over time, not less informed over the time, which implies that the transition matrix has zeros in the bottom half. You know, you have zero probability of knowing less at time 2. You only have positive probabilities of knowing more at time 2. And those kinds of zero restrictions, how you impose those in the Mplus context is described in this paper, which also sits on our website under papers and under the subheading latent transition analysis. And here's a very good statistically oriented paper on slide 45. Where are we? Over here. Slide 46, actually. Beth Rebesine and others at Johns Hopkins wrote this paper in multivariate behavior research, and it's recommended for those who are more interested in the statistical aspects of this analysis. So now we want to give you a few Well, this computer has gone night-night, so we'll stay with the other computer. I don't even think that the fancy pen can wake it up. Well, it could, actually. Maybe now it's gone into it needs to be forwarded by a pen. It's gotten spoiled. So, all right, we'll live with that. We're learning as we go here. So here's one, 48, yeah. Here's one extension. Say that you have a randomized study, but you have an intervention, and you randomize people into treatment and control group, and you measure people on a series of outcomes before treatment, so this is baseline, and after treatment. You can apply, so this is sort of an ANCOVA situation or an ANOVA situation, but in the context of latent transition analysis. And the treatment is intended to influence the probabilities of class membership at time 2 after treatment, lowering the probability of being in the bad classes and increasing the probability of being in the good classes. So that is then illustrated by this treatment-controlled dummy variable influencing the intercept of C2, in line with the dummy variable regression analogy that we have in our mind from linear regression. This is a dummy variable influencing, so it changes the intercept and therefore the mean, that is the logit and the probability of class membership. But we also have this broken arrow, which we agreed on yesterday morning, that implies that the slope of C2 regressed on C1 is different for treatment and control group. So the transition probabilities in terms of the slopes are affected by the treatment. So the B coefficient, in Mplus language of chapter 13, the B coefficients obtained by the on statement are different from treatment and control and as well. And I'm not going to go through that. I don't want to take time because it's a special application. But on slides 49 and onwards, you have the setup for how to do this. I'll just allude to the fact that when you have a treatment control variable, dummy variable like this, to get a very flexible modeling, you can let that treatment control variable be a latent class variable. It's an illustration of a latent class variable that's identically equal to the observed treatment control dummy variable. No measurement error, the first thing we went through this morning, plus minus 15. That's actually automatically handled by an Mplus feature called known class. You can either do it yourself by hand by the plus minus 15 that we talked about earlier this morning, or let Mplus do it by known class, saying that the class for group membership is defined by Tx, the observed variable Tx sitting up there in the names list, being 0 or being 1. And in addition, so you have one latent class variable here, which is Cg, and then you have C1 and C2. So you have 3 latent class variables, Cg, C1, C2. And then you are allowed to have these latent variable specific models, model Cg, model C1, and then model C2. So for instance, for the model Cg, you have 2 classes, 1 and 2, corresponding to control and treatment groups. And we say that the regression of C2 on C1 is different in those 2 classes. So what you're looking at here, you might circle that and give it a name like X and say that that is corresponding to that broken arrow. The broken arrow saying that the regression of C2 on C1 is different for the 2 groups. That's the essence of this example, and then it shows here in utter detail how you can use model constraint to express probabilities as a function of the logit coefficients and express treatment effects in terms of differences in probabilities between treatment and control group for class membership at time 2. But I'll leave that for your own study. Let me instead tell you about another one, another model extension. Now it's awake again. So the standard latent transition model looks like on your left screen, slide 51. That's exactly the one we talked about. But how about connecting this with the modeling we talked about yesterday afternoon? Yesterday afternoon, we talked about a generalization of latent class analysis. If you look at slide 52, the generalization was that we allow for within class severity variation in terms of a continuous latent variable that explains correlations between items within class, and therefore allow for any of the two classes in this case, it allows for a variation in the severity and therefore variation in the item endorsement probability. So you can have a factor mixture measurement model instead of an LCA measurement model at each of the 2 time points, and look at the transition between C1 to C2 while allowing for these continuous latent variables. So that's possible to do in Mplus if you would like to do that. And here's how it applies to Baltimore public school data on aggressive disruptive behavior in the classroom. There are 9 items having to do with how the children in early grades misbehave. And we are dichotomizing these items. For simplicity in this case, you don't have to do that. And the 2 time points, fall and spring of grade 1. And there was an intervention taking place after the fall baseline measure, before the spring post-treatment measure. And for each time point, it turns out that a 2-class, 1-factor, factor mixture analysis model was best fitting. So that's using the techniques that we talked about yesterday afternoon. And here's how it looks in terms of model fit. Conventional latent transition analysis. So you see how quickly it became conventional. We just went for coffee and now it's conventional. And the log likelihood compared to the factor mixture latent transition analysis, we see this likelihood is higher than this. Minus 8600s down here, minus 800s up here. You have a lot more parameters, though, in this more modified model. So yes, it's easy to get the likelihood higher. So we have to let BIC decide, because BIC has the counterbalance of penalizing you for a number of parameters. But still, BIC is lower, much lower, and therefore the preferred model here. And here are the results. Same on both screens. How does that affect the transition probabilities for this alternative model? Conventional LTA says that those who started, this is low and high aggressive level of the student in the fall of 1st grade. Those who started out low aggressive have 93% chance of staying low aggressive in the spring of grade 1, a small probability of transitioning to high. Those who were high have a 17% chance of going down to low, 83% of staying high. Now, if you go with the factor mixture approach, measurement model, then the biggest difference is this last line here, which is bolded. In particular, there are many more people who transition from high aggressive to low aggressive, 41%, as compared to 17%. So this would indicate a stronger treatment effect in that sense than when you use a conventional LTA. So I have not seen this applied. We did this, and we're urging people to take a look at this and maybe see how often this is a useful model. But it is quite a possibility to do that in Mplus. And here, in this case, it actually made a practical difference. So now we get into the guts of this course. So far, we talked about models that have only categorical latent variables in the longitudinal setting. We started out the same way yesterday, We started out with models that are only categorical latent variables, and then we added models that also had continuous latent variables. We're going to take the same route today. So we started with latent class-oriented models, and now we're switching to allowing also continuous latent variables. And one form of continuous latent variable is random effects. Statisticians talk a lot about random effects, and we would just call them continuous growth factors, as we will call them. So we thought that it could be useful to do a short recap of standard conventional random effects growth modeling. So it doesn't have to do with anything mixture or latent class-wise, but just the standard stuff. So this is really topic 3 material in the 8-course sequence, giving you a chance to get into how we look at growth modeling in the Mplus framework before we then generalize that model to also work with latent classes. So I think we have time for like 5 minutes on this slide, because it's an essential slide where you want to, you really want to master this slide to understand how you can approach the growth modeling in Mplus. And as is standard both in statistics and in psychology, we start with the individual and think about how an individual behaves in his or her development over time, and then build up to formulate a model for all individuals in a given sample from a given population. So we can start, we have 3 ways of representing this. We have the top left picture. Y is a continuous dependent variable. X has to do with time, so this could be grade 1, grade 2, etc., or it could be age. And here you look at 3 different individuals. Individual I starting high with respect to Y, higher than the others, and growing at a healthy rate. Individual 3 starting much lower and growing at a much lower rate. And when we talk about this, we're often going to talk about the starting point as initial status, and this is growth rate, but we're also going to use standard, more neutral terms of intercept and slope in the regression of Y on time. So the slope has to do with a growth rate over time, and the intercept has to do with the starting point at the first time point, say. Now you can represent that in formulas if you like that. So you have Y, and here now we start to take an interest in the subscripts, Ti, and we will take an even more intense interest in the subscripts on Monday and Tuesday when we talk about multi-level models, because it's the subscripts that really tell the story. So here you have for time point T, a certain time point here along the x-axis, and for individual I, we're going to write the linear equation, just like linear regression, where we regress on x, but we have then a funny looking intercept. This is an intercept, and this is a slope. Slope multiplying x as usual, plus a residual. And 2 things about the intercept. One is that we're using the Greek letter eta, ETA, like ETA Hoffman, fine restaurant. ETA sub 0 is the intercept, and eta sub 1 is the slope. And it's soon going to become evident why we complicate matters and use eta. But first let me point out that there is one very unique feature here that distinguishes equation 1 from linear regression, and that is that we have a subscript I. If you study linear regression carefully, you never see subscripts I on the intercept and the slope. There's one single intercept, the population intercept, and one single population slope. But here we're saying that those vary across the individuals, individually varying intercepts and slopes. These are what the statistician call random coefficients, random coefficients. Random not meaning haphazard, but meaning varying across individuals. And that's a very interesting idea of statisticians, to make them random, because that picks up on the fact that the intercept here is not the same for the individuals. It varies. It's high, medium, low. And the slope varies across the individuals, high and low. So it allows for individual development over time. And then, in equations 2 here, those random effects here, the intercept and the slope, become dependent variables. You try to explain the variation in the starting point and the growth rate, again by a linear equation regressing on some W covariate, a characteristic of the individual that explains his or her starting point and growth rate. And here, again, it's a linear regression. Here, the intercept is called alpha, and the slope is called gamma. We love the Greek. And in this case, you note that it is regular regression in the sense that you do not have subscripts I anymore. They're only part of the first equation 1. But it's regular regression here, apart from the fact that the dependent variable is not an observed variable, but this individually varying random effect. Looking at it this way, this is equation 1 is the level 1 equation in the multi-level setting that we're going to talk about on Monday. And equations 2 are level 2 equations. So equation 1 talks about variation across time, Ti is a subscript. And equations 2 talks about variation across individual, having only subscript I here. So you have the 2 levels of the model in this way. Now in the latent variable framework of looking at this, these random effects, eta 0 and eta 1, are considered to be latent variables, which is natural. You cannot observe them in the data. They're not measured. So they're latent, and they do vary across individuals. So they are latent variables. And we may draw a picture of it in model diagram. For 4 time points, you have 4 y variables. And the variation in those, that variation is explained by the growth factors, we call them now, the intercept eta 0 and the slope eta 1, influencing each of them. You see from equation 1 that eta 0 influences y, and eta 1 influences y as well. And this would then be the structural part of a structural equation, a measurement part of a structural equation model, corresponding to equation 1, whereas the regression of etas on W, corresponding to level 2, would be the structural part. So level 1 is the measurement part, level 2 is the structural part. And you have to then also note that the coefficients here, if you look at this model, it's sometimes called a structural equation model that is called mimic modeling. Mimic, you have multiple indicators and multiple causes of latent variables. And this is then the factor loading part in the SEM CFA, confirmatory factor analysis setting. And the factor loadings are very specific. Eta 0 influences y at each of the 4 time points the same. There's an invisible 1 here multiplying eta. And so all of the loadings for eta 0 would be 1, fixed 1. And the loadings for eta 1 will be the x values, the time values sitting on these coefficients. So all of the loadings will be fixed. So it's a very peculiar CFA, confirmatory factor analysis, SEM model, that is very restricted, but it's suited for these kinds of growth models. And we like to formulate models this way in the latent variable framework because it really lends itself to interesting generalizations. You can immediately think of very many. For instance, the covariate, if it has measurement error, maybe it's better represented as a latent variable with multiple indicators. Or the dependent variable may, instead of one measure, be a latent variable indicated by several measures. Or the covariate may have a direct influence on the outcome at certain time points, which would correspond to that measurement non-invariance differential item functioning that we talked about, et cetera, et cetera. You're going to see a whole host of generalizations as we go on this afternoon. So this is what we spend a whole day on in topic 1, 2, 3. And you may want to watch that video if you haven't already. Here is how we look at it, multi-level modeling, and well, different frameworks. We talk about multi-level modeling, for instance, represented by the US HLM program. We also talk about this kind of modeling in terms of mixed linear modeling, represented by SAS-Proc mixed. We talk about this kind of modeling in the structural equation modeling world. And here in the square is the Mplus way of looking at it, which is the latent variable modeling perspective. And that perspective is more general than the SEM perspective. As we described, it has to do with certain things that the SEM modeling cannot handle, SEM being limited to mean and covariance structure modeling, which is not always relevant, not always sufficient for these models. HLM, multi-level and mixed linear modeling represented by those softwares are fairly similar and overlap to some extent with SEM, but can do more than SEM. Most of Mplus can handle, Mplus can handle most of the models in these frameworks, but there are some things in those frameworks that cannot be handled by Mplus yet, such as crossed random effects modeling. But we have these arrows going up where the Mplus framework keeps expanding. So maybe next year when we meet, say in a training course in Barcelona, how's that? We will have further developments to report for you. Now, we like to work in this latent variable framework for several reasons. We can allow for very flexible curve shape handling. You notice that those time values x actually were factor loadings in this latent variable approach. In the SEM approach, that is, you can estimate those time steps, which makes for possibility to estimate very flexibly shaped curves. But at the same time, you can do what cannot be done in SEM in that framework. You can handle individually varying times of observations. So we spend some time when we talk about this to make the distinction between time represented by parameters in the first approach and time represented as data in the second approach. And in the multi-level and mixed linear model approaches, time is data, but it doesn't need to be data. It can be parameters when you don't have individually varying times of observation. We're not going to focus on that too much today. But once you're in the growth latent variable framework, you can also do things that you do in the structural equation modeling latent variable framework quite often, namely regress the random effects onto each other. So you can see how the growth rate is influenced by the initial status, how the slope is influenced by the intercept, for instance. And we give several examples of that. And it's very easy to deal with multiple processes. You know, you're not only looking at how aggressive disruptive behavior develops over time, but perhaps how achievement develops over time over the grades. You can easily deal with modeling of zeros. We talked about that in terms of zero inflated Poisson yesterday. The preponderance of zeros, a large group of individuals who haven't started with the behavior yet. You can easily deal with multiple populations, males, females, multiple cohorts, and multiple indicators of latent variables easily handled. And the growth model may only be one small part of a bigger model. So the growth model is embedded into a bigger model. And what we're going to focus on today quite a lot is the case where you generalize to allowing for categorical latent variables, growth mixtures. So in addition to the continuous random effects, you have categorical latent variables. And we're going to talk quite a lot about that. Now, let's take a deep breath here and look at We have, well, let me back up. We have now introduced growth modeling in Mplus through, and we're going to talk more about that actually on Monday, talk more about issues of growth modeling in Mplus. There are two ways of doing growth modeling, as a wide multivariate approach versus a long univariate two-level approach. We're going to talk about that on Monday. I introduced growth modeling here in the latent variable context for continuous outcomes, but let's get familiarized with categorical outcomes as well, since we need to practice our skills in dealing with categorical variables to help us when we go to categorical latent variables. So you have this formula page here, and we're talking now still about individual differences in development over time, but now it's differences in probabilities over time. So an individual has different probability of engaging in an activity at different time points. But we're going to still work with the logistic model. So a logistic model deals with the log of the odds. So log of this probability ratio, u equals 1, u equals 0, as a function of growth factors and observed covariates. Here it is a quadratic model, so you have an intercept and a linear slope and a quadratic slope, eta 0, 1, and 2. So it's a quadratic model here for simplicity, for generality. And we assume that these growth factors then are related to a covariate or several covariates for the individuals, W, in the same fashion as we looked at before. So up here on level 1, we are considering a logistic regression, whereas on level 2, since the dependent variable is continuous, we're considering a standard linear regression, right? Standard, quote unquote. It's sort of standard because the dependent variable, although continuous, is not observed. But that's not an essential distinction. The essential matter is if it is categorical or not. I'm not going to talk about this, and I'm instead going to let Linda talk so you can hear some other voice for a while.
Okay, so we're going to take a look at an example of a categorical growth model. And just to remind you, this is just standard growth, not multiple classes, no type equals mixture. So just to give you a little bit of an introduction into growth modeling before we go into latent class growth analysis and growth mixture modeling. So the example looks at schizophrenia data from the NIMH Schizophrenia Collaborative Study. And we have 64 patients who use a placebo and 249 on a drug for schizophrenia. We measure them at baseline and at weeks 1 through 6. The analysis we're looking at is the dependent variable is severity of illness at weeks 1, 2, 4, and 6. And you'll note that these are not equidistant measures. We don't measure 1, 2. We measure 1, 2. We don't measure at 3. We measure at 4, but not at 5. And then we measure again at 6. And the way that the non-equidistance is taken into account in the growth model is by having the time scores not be separated by equal distances. And I'll show you that when we look at the input. So in this example, the time scores are not data, they're actually parameters in the model. So Bengt mentioned that it can be either, but here there are parameters in the model. And on the screen here, we see what it looks like, actually the results. So we have two groups are people are randomly assigned to placebo or drug. And we can see that because they're starting in the same place. And for the placebo group, we see that over the 6 weeks, there is a decrease, also for the drug group. And we're interested in estimating this model and seeing the regression of the growth factors on the drug, the treatment group. So we'll keep that over there for now to refer back to. Here's a picture of the model we're going to estimate. So we have the illness measured, the severity of the illness measured at week 1, 2, 4, and 6. So we have 4 repeated measures. We have I, which is the intercept growth factor, S, which is the slope growth factor. And both of these growth factors vary over individuals, but the intercept varies over individuals and the slope. And we regress these 2 growth factors on the drug, so on the treatment. And because we have randomly equivalent groups, we expect that people will start in the same place so that I on the drug will not be significant, as we see over there on the other screen. So we randomly assign people to drug and placebo, so they should be starting at the same place. And then we regress, the treatment effect will be the regression of the slope on the drug. So the growth on the drug will be the treatment effect. Now, I think I want to go back to the slide Bengt had, slide 57, so you can see the relationship to between the Mplus language and also the input. So on the right screen, we see the usual input things, categorical R, so we're specifying that the severity is a categorical variable. Estimator equals ML, so we're using maximum likelihood estimation. In Mplus, the default for categorical outcomes is weighted least squares estimation. So we've commented out estimator equals WLSMB just to remind ourselves basically to mention that to you. Okay, because I don't want this to be in the way, I think I'll put 57 here. And 66 over here. So at the bottom of this slide, I show using the factor analysis language to specify the growth model. And that's what we had when we first started Mplus. Subsequently, we created a special growth modeling language, which is shown in the model command above. But I think the factor analysis language relates better to the picture that Bengt has, so I wanted to show you that also. So for example, as I mentioned yesterday, the by option is short for measured by, and it's used to name a continuous latent variable and define it by its specification. So here we say I by illness 1 dash illness 6 at 1. And so what we're doing there is fixing all of the factor loadings for the intercept growth factor to 1 as shown in equation 1, where there is an invisible 1 here in front of the intercept growth factor. So here's the intercept growth factor, and you can see that it's pointing to everything, but if you go to the formula, you know that those values are all fixed at 1. So that's the I by fixed at 1. And then for the slope growth factor, it also has all of the outcomes as dependent, as factor indicators. But for that, we give time scores. And the time scores are shown here in the X. So that varies over time, and that's the time score. A time score of 0, the time point where the time score is 0 defines the intercept growth factor. In our example, you can see I have S by illness 1 at 0. So we're saying that the first time point defines the intercept growth factor. So sometimes people refer to that as initial status, the first time point at 0. And the second time point represents that we measured the persons at time 1 and 2, so 0, 1, but then we didn't measure until time 4. So we fixed the time score here at 3, and then we measured again at 6, so we fixed that to 5. So the fact that the difference between 0 and 1 and 1 and 3 and 3 and 5 are not the same distance, some are 1 and some are 2, represents the fact that the measurement occasions in the repeated measures of the outcome were not equidistant apart. So, you know, when you create time scores, they need to reflect the measurement occasions. So if you measure people in grades 1, 2, 3, and 4, the time scores will be, if you have initial status, 0, 1, 2, and 3. But if you measure them in grades 1, 2, 3, and 5, they'll be 0, 1, 2, and 4. So the time scores reflect the non-equidistance of measurement. Another part of the growth model, and we're looking at the categorical growth model. There are two different parameterizations of the growth model that are used in Mplus. One is for continuous outcomes, and the other is for categorical outcomes. And so for categorical outcomes, we hold the thresholds of the outcome equal across time. So we refer to this in square brackets, illness number 1, illness 2 number 1. So these are the first thresholds, illness 4 number 1, $1 rather, and illness 6 $1. And the 1 in parentheses after that says, all of these thresholds will be held equal over time. So that's part of the parameterization of the growth model. When we hold these equal over time, and the alternative would be to fix them to 0, but when we hold them equal, then the intercept growth factor mean is fixed at 0. And in this case, it's actually an intercept because it's a conditional model, and the slope growth factor intercept is free to be estimated. And then this is not part of the growth model. And this we comment out. This refers to scale factors, but that's only related to the WSMB estimator. So basically, this shows you what goes on behind the scenes in Mplus when you use the growth modeling language shown in the model command. So the special growth, and I recommend using the special growth modeling language simply because we have different defaults for that language that are more applicable to growth models. The BI language is really a factor analysis model, and therefore has defaults that are more appropriate for factor analysis, so starting values and such. So anyway, in the special growth modeling language, you use a bar. To the left-hand side of the bar are the names of the growth factors. To the right-hand side are the time scores. So illness 1 at 0, illness 2 at 1, illness 3 at 3, illness 6 at 5. The number of growth factors on the left-hand side of the bar define the type of growth model. If you have 1 growth factor, it's an intercept-only model. If you have 2, it has an intercept growth factor and a linear slope. And if you have 3, you have, in addition to that, a quadratic slope, 4, a cubic. So the number, it doesn't matter whether you say I or S on the left-hand side. What matters is how many names you give. The first one is assigned to the intercept growth factor, the second one to the linear growth factor, and the third to the quadratic growth factor, et cetera. So we'll be seeing this language now when we start looking at latent class growth analysis and growth mixture models. So let's see if there's anything else here. So here's our special language. And what it does behind the scenes is everything you see down here in the first 4 statements. And then we want to regress the intercept and slope growth factors on the drug or the treatment. And so we do that using the on statement. So this is probably a lot to take in, given that we spend a day on it, but anyway, that gives you a slight idea of how we do that. And then we have our results, the normal tests of fit. And then what we're most interested in is the regressions. So here are our estimates, and for those new people here that are new, the first column in the results show the parameter estimates themselves, and these are the raw estimates, not standardized. Then we show the standard error of the raw estimate and the ratio of the estimate to the standard error. These two standardized columns are from an old output. We now give standard errors for the standardized output, and when you ask for that, that comes in a separate section below the regular results. But what we're interested in here is when we look at I on drug, we see that that effect is not significant, and we wouldn't expect it to be because we randomly assign people to treatment and control, and therefore we wouldn't expect them to differ on the intercept growth factor. The treatment effect is S on drug, and it is significant. We see that in the third column because we have a value greater than the absolute value of 1.96. We see it's a negative relationship, which implies that taking the drug reduces the symptoms of the people, as we saw in the first picture. And we show the intercepts. This was fixed at 0 as part of the growth. The intercept of I was fixed at 0 because that's part of the growth model parameterization for categorical outcomes. The thresholds are held equal, as you can see here. They're all negative 5.706. That also is part of the parameterization of the growth model. And here we have a residual variance for each of the intercept and slope growth factors. Note that because this is a conditional model, we have a covariate. Instead of estimating means and variances for the intercept and slope growth factors, we estimate intercepts and residual variances. So if we had a model without covariances, we would show means and variances here for I and S. But when you have covariates in the model, it's a conditional model, and intercepts and residual variances are estimated instead of means and variances. So this is the example of the categorical growth model. And then I'll let you start with the references. And anything else you want to add?
So this is a good warm-up example for where we will be heading for the rest of the day. And just to practice a little bit further, if you look at the slide 68 here, Linda pointed out that when we have a conditional model, and by conditional we mean, we use the term from the multi-level literature, meaning that you have covariates. An unconditional model does not have covariates. Covariate being denoted W in our first generic slide. So here we have a covariate. We have a 0-1 control treatment dummy variable. So let me ask you, what does it mean that this intercept for S is negative significant? Say that again. Everyone decreases? Two groups are decreasing. Yes, well, that's getting close. But remember, intercept for S, it's very confusing. You have a slope that has an intercept. Try to say that fast. So S is regressed on a treatment control dummy variable. So the mean, you can ask yourself, what's the mean of S? Well, it's a function of the intercept and the slope in S regression onto the treatment control dummy variable. Now, when the treatment control dummy variable is 0, which it is for the control group, the intercept for S is actually equal to the mean of S. So it's only when X is 0, it's only the intercept that contributes to the mean of S. So this says that the control group has a negative slope already. So it's talking about the control group here. The placebo group has a placebo effect, which is significant, which is often seen in schizophrenia and even more so in antidepressant studies. So patients get better by taking a sugar pill, maybe by the attention of the personnel that they're interacting with. So that is an example of where the intercept becomes a mean. And then on top of that, we have the S on drug effect here, which is significantly lower. So this is a significant difference between the slopes of that and that curve. Just to exercise that a little bit more. Now, if you want to read about this, I find that growth modeling with categorical outcomes is often not treated very thoroughly in books, but there is one book here, Fitzmaurice and Laird and Ware from the Northeast in the US. They have written a nice book which is fairly applied and does treat the categorical case. There are articles by Bob Gibbons and Don Hedeker, biometrics, and some early attempts by me doing this in an edited book. And a technical web note. We have web notes on, not quite papers, although this is quite a paper, on our website describing how to think about this from an Mplus perspective. So now let's start to generalize a little bit, and instead of going into detail, let's just talk in more general terms. Here's an interesting model which draws on all of our newfound knowledge about categorical variable analysis. How many of you have in your data seen distributions for the variables that look like this? Yes, that's a common thing, right? And you're ashamed of it, aren't you? Because it's not normal. But you can come out of the closet now, because it's something that's called two-part growth modeling. And it takes a variable like this and splits it up into two parts. One part is a dichotomous saying, do you engage in the activity or not? And the other part, if you engage in the activity, how much do you engage in the activity? So this could be frequency of heavy drinking. And most people in the national general population sample say they don't engage in heavy drinking at all, so they are in this bar. But a portion of them say they engage in heavy drinking, and for them you can actually then report and study the amount, the frequency of the heavy drinking. So you split the variable into two parts, and then you do a growth model for each part. Here's the binary part that Linda just gave an example of for schizophrenia. You have the growth factors, in this case intercept, linear, and quadratic, and you have the binary outcomes. And that is for doing heavy drinking or binge drinking at all, whereas this part up here is a regular continuous outcome growth model, quadratic, three growth factors, describing the amount of heavy drinking when it occurs. So this idea was presented by Olson and Schaefer in JASS at the Journal of the American Statistical Association in 2001, and we thought it was a great idea, so we put it into Mplus. They actually describe it in different terms, but if you simplify it, you can describe it as what we will call a parallel process model. You have two processes going forward. So this is a very, very special case of a parallel process model, where in this case, the processes are tied together so that when the U variable at the bottom, when the U variable is 0, the corresponding Y variable is missing. When you don't engage in the behavior, you don't have any frequency of that behavior. So you can ask for, in Mplus you have the setup data 2 part, which data 2 part, that option, creates from a variable like this creates the two variables ready for two-part growth modeling. And the interesting thing is then that this is better than many other alternatives, including working with censored normal variables, because of this idea that the background variables, what we call W, the covariates, can influence the two parts differently. So the decision to engage in heavy drinking can be affected by a different set of variables, or at least differently by the set of variables, than the amount. And that's been picked up in writing that has to do with the intervention studies. So the intervention may have an effect on one of the two processes, but not the other. And then, you know, if you want to go advanced, you can extend this to mixture modeling. So what's new here on the right screen are the categorical latent variables C for the Y part and C for the U part. Because one weakness, I think, in this two-part growth modeling is that it is assumed implicitly that at any age, everybody, say at age 20, everybody is on the same growth curve development, irrespective of when they started drinking, irrespective of how early they started drinking. And one could argue substantively that those who started drinking heavily at an earlier age may be on a higher average trajectory at age 20 than those who just started drinking a few years earlier. And to capture that, you may need a growth mixture model, which we're going to spend quite a lot of time on today, this afternoon in particular. And here's an advanced version of it where you have a mixture model for each of the two parts. We're not going to talk about that more than just saying that that exists. So we have the extensions of two-part modeling with distal outcomes. It can actually be parallel process two-part. So it'll be 4 processes going forward, say. And you can have mixtures, as we talked about. You can also generalize it to multi-level. And we have a factor analytic counterpart to this, a two-part factor mixture model, where the two-part idea, you know, the heavy preponderance of zeros ideas is captured by mixtures, captured by two-part on top of mixtures. And that's a paper by a former student of mine and I that's coming out in structural equation modeling sometime soon. Anyway, extensions. Let's see. What do we have now? Here is a new topic. We are sort of circling our way through the different topics, just to give you the roadmap again. We started this morning with models that have only categorical latent variables. Essentially, this morning was the counterpart to yesterday's latent class analysis, changing that into the longitudinal setting so that we have latent transition analysis, only categorical latent variables. Then we switched gear and talked about random effect growth models. I gave my introduction. Linda gave her schizophrenia example. That had no categorical latent variables, only continuous random effects. Now we sort of come back, have a little bit of flavor of what we talked about this morning. We're going to talk about latent class growth analysis. And that is a growth model which is different from the latent transition model, and in a way more similar to the growth models I've just talked about, with one important difference. And Linda's going to tell you what the important difference is. But you want to keep, so there's several distinctions made here. Only categorical latent variables, only continuous latent variables, and the combination, that's one distinction. Another distinction is, do you have an autoregressive model or do you have a growth model? Autoregressive models is where the behavior at time 2 is influenced directly by the behavior at time 1. Late transition analysis being an example of that, as opposed to growth models, where in growth models the behavior at time 2 is not directly influenced by time 1 behavior. Y1 does not influence Y2, but Y1 and Y2 are influenced by the growth factors. That's a different thinking, right? And you have to pick the model that suits your data the best. We talk about that a lot in topic 3, and we try to cover it enough here too. So you have to ask yourself, how you behave today, does that depend on how you behaved yesterday or last month, or does it depend on growth factors? So for instance, in a learning situation, the growth factor idea might be more relevant. How much you learn, the learning process is what influences how you perform today, not how you performed last month. That's just a test result. Maybe if you had a good test, you're less nervous today, and that would be a direct effect. But otherwise, it's the growth process. Whereas in other applications, it's exactly what you did 1 month ago that influences what you do today. For instance, if you smoked a lot a month ago, you're likely to smoke a lot today. And it's not a growth process, it's more a dependence process. So even though we now get back to latent class thinking, the key thing is that we are in a growth setting. So we are not doing the latent transition analysis, we're not doing the autoregressive, we're doing a growth model. So do we switch to you right away here?
Sure.
Okay.
Okay, so now we're turning to latent class growth analysis, which is a model that contains both categorical and continuous latent variables. So this is a longitudinal model where we have a single item that's measured repeatedly, as you can see on the screen. And we hypothesize that there are different trajectory classes, that not all individuals develop on the outcome that we've repeatedly measured in the same way. So as we saw yesterday, that we had different classes of people, not over time did they differ, but they just differed in how they looked as far as on a profile of a set of variables measured at the same time. So now, yesterday was cross-sectional, today is longitudinal. So we're transitioning to this latent class growth analysis, which is referred to as LCGA, and it's a longitudinal analysis. So what we want to do, what our goals are, is to estimate the trajectory shapes. So we want to do a series of analyses where we see how many classes look correct. This can be based a lot on theory in this situation. And we want to see what the class probabilities are. So how many people have each of those different shapes. Once we've determined the classes, we want to understand class membership, just like in latent class analysis yesterday. We want to understand what covariates explain the different growth trajectories. And we want to classify individuals. We can have this, LCGA can have one growth process or many growth processes. It's not limited to a single process. Now, the example that we're going to look at is 411 boys. It's taken from, it's a single process. So as I mentioned, we can have single or multiple. So we're going to look at one growth process. And it's taken from Cambridge delinquency data. 411 boys is the sample. Well, I guess N is actually 403. Ages 10 to 32. We're using ages 11 to 21 in our analysis. And the outcome is the number of convictions in the last 2 years. It's modeled as an ordered polytomous variable, so we're still in the categorical equals framework, but instead of binary, we're now looking at a variable that has 3 ordered categories: 0 for no convictions, 1 for 1, and 2 for more than 1 conviction. And the sources, the references are shown at the bottom of that slide. So yesterday, if you take a look at the left side, we show a latent class analysis model, which we looked at yesterday. To the right is the LCGA model. In the LCGA model, we have our outcomes repeatedly measured, shown in the squares, and then our growth factors. And here you see we have I, S, and Q. So we're modeling, we have a quadratic growth model. And we have our categorical latent variable C. It's pointing to I, S, and Q, which means that the means of those variables are going to be allowed to vary across classes. If you look at the bottom, you can see that we have the number of parameters for LCA versus LCGA, for a binary U versus the 3-category U that we're looking at. So in the LCA for binary, we have 35 parameters, and for 3-category, 68. For LCGA, 11 for the binary, and 12 for the 3-category. So you can see that the LCGA is a much more parsimonious model, which would be a reason, to use that model. Here are the results of the LCA. And actually, doing an LCA as a first step, even though you're interested in an LCGA model, is a good idea, because you can see from the LCA results on the left screen here, we found 3 classes: a normative class, which is most typically found, and then 2 other classes, which you might say, one that starts low, goes up and comes back down, one that starts high, goes up and stays higher. And so these 3 classes, although they look somewhat ordered, there's a large difference between class 2 and class 1 in where they start and also where they end, which makes them different enough to consider as separate classes. But you also see here over time, and time is on the x-axis here. This is not just like we saw yesterday in LCA, a set of different variables along the x-axis. This is the same variable measured repeatedly across time. And you can see that there does seem to be a quadratic shape. So by doing an LCA, you can get some sort of an idea on what the shape of your growth curve might be. So here we see quadratic. That looks quadratic. You can see for the normative class, it doesn't. But what would happen here is if you specified a quadratic, your estimates for the linear and the quadratic part would just be 0, the means. So this is the results of that, LCA. So based on that LCA, we decided to take a look at a quadratic LCGA. And one of the special things we're going to be talking about the LCGA model now, and then we're going to extend that to a growth mixture model. And the difference between an LCGA model and a growth mixture model is that an LCGA model does not allow variability of the growth trajectories within class. So if you find 3 growth trajectories, within each class, every individual in that class has the exact same values. Whereas in a growth mixture model, we also are looking for growth trajectories, but within each class, we allow there to be variability on those growth trajectories. So everybody doesn't have the same values. So here we're specifying an LCGA model. And you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 time points that we're considering. And we have one categorical latent variable, C. And these we're using only, our used variable statement shows that we're only using the U1 variables. We're specifying that they're categorical. They have 3 categories, so they're ordered polytomous variables, and the program will know that. And we're specifying that we're going to estimate a model with 3 classes. We specify type equals mixture. When you have categorical outcomes and you say type equals mixture in Mplus, we do not, for this growth model, estimate any variances. So it's a very, there are no dimensions of integration. If categorical outcomes and continuous latent variables, like we said yesterday, each continuous latent variable is one dimension of integration, but it's not if the variances are fixed at 0. And in LCGA, the growth factor variances are fixed at 0 and the growth factor covariances. So we have no dimensions of integration. And that's the default if you say type equals mixture in Mplus. If you want the variances to be estimated, you have to add algorithm equals integration to the analysis command. Okay, so let's take a look at the model command. And you can see that here we use the special growth language. So on the left-hand side of the bar, there are 3 names, 3 variable names, I, S, and Q. That implies that we want to estimate a quadratic growth model. And then you can look at the time scores and you see we have -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, and 4. So we have, as I mentioned earlier, the time point where the time score is 0 defines the intercept growth factor. So what we're doing is we're centering this growth model at U17 or U17. So this is just a different way of defining the intercept growth factor. Instead of initial status having 0 be at the first time point, or final status having it be 0 at the last time point, we're doing it in the middle, and that's how the time scores are reflected. So the time scores, the 0 is here. So it's just a matter of subtracting. Like if you had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you wanted 7 to be 0, then you would make 7 0. 7 minus 7 is 0. You would subtract 7 from every other time score to get the time score to use in the analysis. Here we are asking for plots. The series equals U11 to U21 with S in parentheses means take the x-axis from the slope growth factor time scores. So it will use these time scores on the x-axis. Now I'm going to go through the results just standing here and showing them to you on the screen over there. So we get the results for each class. And the first results we see, I bar. That's just showing us that we have fixed all of the factor loadings for the intercept growth factor at 1. Then on the next screen, we show S bar, and we're just showing the time scores that we see over here, the -6, -5, -4, et cetera. So that's just it's always a good idea to take a moment to go through your output carefully and make sure it looks like you got what you asked for. And then we have Q bar. So what Mplus does is the quadratic time scores are simply the square of the linear time scores. So Mplus squares those values for you automatically because you've used the growth language. In class 1, the means of IS and Q are free. The thresholds are free, but they're held equal to across the other classes. So let's take a look now at latent class 2, where we're not showing the full output, we're just showing Q bar and the means and the thresholds. So if you look at the thresholds for class 2 and then you go back and you look at the thresholds for class 1, they're equivalent. And then latent class 3, we also don't show the full results. Now, what's important that you didn't see in these results is we saw means for the growth factors, but we didn't see any variances, and we didn't see any covariances, because LCGA is a model that estimates growth trajectories, but does not allow any variability on those trajectories within class. So the variances of all the growth factors and their covariances are 0 for this model. And what we're going to go on later today, and we're going to look at growth mixture models where the variances aren't 0. And that's the only difference between LCGA and GMM, are the growth factors having variances and not having variances. Not having variances for LCGA and having it for GMM. And we'll philosophize a little bit about that when we get there. So now we have the results of our LCGA. So here's the LCGA at the bottom. We have our results for our LCA, 68 parameters, a BIC of 2472. Here we have 12 parameters, a BIC of 2215. And although the 3-class LCA has a slightly lower log likelihood, there's a huge, or higher, I mean, log likelihood, there's a huge difference in the number of parameters. So one could conclude that this better fits the data. So what do we have? We have similar growth trajectories. They look similar to the classes we saw in the latent class analysis, where we ignored the fact that the variables were repeated measures and treated them more like separate variables. But we have the class 3 down here, which is the normative class. Class 2, which starts a little higher, goes up and comes down. And then class 3, which starts, or class 1 rather, which starts a lot higher, decreases, but does not decrease to a particularly low point over age. So we have to remember these are over ages. So here the peak is around 16. And remember, these are the number of convictions. 0 represents no convictions, 1 represents 1 conviction, and 2 represents more than 1. So, and the y-axis is the probability of convictions. So this is an example of a latent class growth analysis, where we're interested in finding out if there are different trajectories for different people, or another way that we talked about it yesterday is, do we have heterogeneity in our data? You know, do our data come from a single population or multiple populations? And by analyzing the data as a single population, are we missing certain things because we're not taking into account the heterogeneity? And I would say that that probably points to the fact that we are. But once again, and you're next here, but all of these analyses, and there's some criticism of the analyses, and basically you can criticize any analysis. You can criticize the use of a mean. I mean, there are people who use a mean with really skewed data, and that really isn't an appropriate central measure tendency in that situation. So there's pretty much not any statistical method that isn't abused and that can't be abused. So I think what we like to stress here is that these are methods that help you get a lot more information out of your data, but they require you to be very responsible in using them and very careful, and to have the knowledge behind the methods so that you use them correctly.
Thank you.
You're welcome. Whoops. What?
You're off.
Okay.
No, I mean, your microphone is off.
Right.
I hope. Okay, just a little repeat on that slide 77, which I think is neat. So you're fooling the latent class analysis. Latent class analysis doesn't know if your variables are 11 different variables or if it's one variable at 11 time points. LCA is not aware of any time progression, and that's all right. We can still find classes, and we can then find approximate growth shapes that we then implement in the LCGA. Because it would be very hard, it's very hard to get a notion of growth shapes from categorical data. For continuous data, when we teach topic 3, we talk about plotting individual curves for all individuals to get a notion of the growth shape. Is it linear, is it quadratic, or what? But for categorical data, you have a bunch of zeros and ones, or 0, 1, 2 in this case, and it's almost impossible, it is impossible to tell what the growth shape should be. And therefore, it's good to have an approach like this LCA to more exploratorily decide on the growth shapes. So that's an interesting first step. Now, let's go forward then, and yeah, the time is time for questions, so I will just briefly whip through a couple of comments here. Multiple process LCGA is possible, said Linda, and we have an example by Christy Jackson, Ken Shear, and Phil Wood, college sample of looking at AUD, that's alcohol use disorder, and TD, which is tobacco use disorder. So two processes going forward at the same time in a college sample. And it's drawn, you could draw the picture like this, very similar to the two-part model, two processes, alcohol use disorder process, linear development at the top, and tobacco use disorder, linear development at the bottom, and two latent class variables that are correlated, so one for each of the processes, and you can look at the relationship between the two latent class variables here and see how alcohol and tobacco use go together. So that's quite possible. It's still an LCGA in the sense that you only estimate growth factor means and not growth factor variances and covariances. And Dan Nagin has written a whole bunch of papers on this and is a proponent of the LCGA approach. And with that, we've come to a great starting point for this afternoon after lunch, and are now ready to take your questions, where the microphone is here, and you'll be the first.
Okay. I have a question concerning slide 88.
88.
There in the figure you give a probability of conviction, and if I remember correctly, you said that the the observed variables had 3 categories.
Right.
Being or having been convicted once in the last year or 2 years?
0, once, or more than once.
Yes. So shouldn't there be probabilities to be convicted or to have been convicted once and to have been convicted more than once?
Great pedagogical question.
Exactly, and you can answer that. You summed the top 2 categories, is that true, or? Okay.
Yeah. So,
You can do it in different ways, but I don't know what you did in this way.
So 0 is no conviction, 1 is once in the last 2 years, and 2 is more, 2 or more.
Right.
So in Mplus, then you get a choice of plotting either the highest category or the sum of the 2 highest. So in this case, it is the sum of the 2 highest. So conviction at all is what's shown here. So you have that option of looking at either the highest or some of the couple of highest. And by the way, I should say that this corresponds to Terry Moffat's idea of adolescent-limited antisocial behavior versus life course persistent. So these continue misbehaving even at a higher age. So they would fit in with her theories. Adolescent limited and life course persistent development. Yes, where's the microphone?
I have 2 questions. One is for slide 66. There you, in the alternative language, you have S by illness, I by illness, and all set to 1. Right. Why not set them to 0 if they are intercepts and you want them to out of the equation? Why are they set to 1?
Let me do 57.
Yeah, it's good to get that clarified.
Right, so in equation 1, those factor loadings are for eta sub 0, and there's an invisible 1 here. They're all fixed at 1. So they aren't intercepts, they're factor loadings. And they're all fixed at 1 according to the model.
So how you started off in life affects you for the whole life.
Oh, how depressing.
What? I have another question. It's for slide number 70.
70?
Yeah, 70. And that's a correlation between the 2 intercepts. And why are they correlated and the other growth factors are not correlated?
Great pedagogical questions. Is this the microphone? No. Yeah, so the question is on slide 70 about this double-headed arrow, and why are the other growth factors not correlated? They could be, but the idea is that most often it is the intercepts that have the strongest correlation. You want to have a correlation between them. Say that you had no background variables, and then the only reason the 2 processes would correlate would be through these residual correlations across growth factors for the 2 processes. And it, you know, if you have a high tendency to engage in heavy drinking, if the probability is high for engaging in heavy drinking, the amount is probably high as well, is the idea. So they should be correlated, otherwise there would be no use for doing this model. But you're right that you may want to correlate more of them, but often it's not needed.
I have 2 questions. First about the right hand slide. I'm not sure if I understood well. Did you assume here that the slope is constant for every individual over all time periods?
So
if the slope is not constant for all individuals, you have the subscript I.
Yeah, for every individual.
Say that again.
If the slope for every individual is the same over all time periods.
The slope
But
is
not
different
this model.
for individuals, but the slope can change over time if you want to. We have something called piecewise growth modeling, so you may at first grow very slowly and then grow more rapidly. We handle that by, say, piecewise growth modeling. But in all cases, the slope, the growth rates are allowed to be different across individuals.
Yeah, across individuals, of course, but if I see the diagram there, you have only one direction. It doesn't go up and down over time.
Okay, yeah, so this is illustrating linear growth, and then you would only go up or down.
Yes.
But if you want to go up and down, then maybe you want to have a quadratic growth function.
And then you would have plus eta
So you would have
qi or something.
that's curved like that.
X squared t.
Okay.
And if you want to have an even richer representation of going up and down, perhaps, then you could use piecewise growth modeling.
And this is all in the day 3 course in detail, and that course is on the website, and the course handout's on the website. So if you want more information about that, I think a really good idea is to take the course handout off the website and listen to the course, because we go into really a lot of detail on that.
Do you want to say something more about that?
About the other, you divided this distribution in the middle into separate patterns. The upper pattern, which value had the first category? It's 0 or it is missing?
I think you're asking about why, when U is equal to 0, when U says you don't engage in binge drinking, in heavy drinking, in that case the Y is missing. And that's the correct way of doing it, because then you are actually doing the Olson and Schaefer growth modeling. You get the likelihood that they are considering. So, and that's what the data 2-part feature of Mplus gives you. It provides missing here when U, the corresponding U is 0.
Is missing.
And in the user's guide, if you look at data 2-part, there's a whole explanation of how we do this. And so you could read about that and then see more. It's more thorough than what we're saying here, I think. Don't you, Bengt?
Yeah.
I also have 2 questions on slide 57 that you already have
57.
up. The one that you have on the right. I don't understand the arrow
right?
going from the slope from eta 1 to y1.
Slope from eta 1 to y1.
Yes.
Okay, so that's x sub t represents those slopes.
So x, so the time value at the first time point is what that slope is. It is often fixed at 0, which means that you could delete that arrow. But this is sort of the general representation.
All right. And then on slide 82.
Slide 82.
How do I interpret the negative intercept? The mean of the intercept is
So
negative.
slide 82, how do you interpret the negative mean for the
For
intercept
class 1, yes.
growth factor? Typically, you don't give interpretation for means of growth of intercept growth factors. And they typically are related only to the level of the variable, say the measurement scale for a continuous variable. In this case, if you put the mean together with a threshold estimate, you'll be able to compute the probability for U in a certain class. So it's only indirectly. I would not attempt to interpret that. I would only use probability calculations. I would interpret this, that there is positive growth, first initially positive and then negative downturn, this shape that we saw. But I don't place much emphasis on the mean of the intercept, no. Yes?
How do you handle with...
Could you, let's use the microphone for the others.
How do you handle with missing data in this case? Mplus do?
How do you deal with missing data?
Yeah, in this case or in latent class growth modeling.
So do you mean missing a whole time point? Like
Not, but maybe one time point for an individual.
So within a time point, missing on an individual?
Yeah.
Yeah.
Does the individual...
Yeah, we repeat ourselves here, but in topic 3 or topic 4, I can't remember which, we actually spent a couple of hours on missing data handling, but this is estimated by maximum likelihood, and missing data is then following the so-called MAR assumption, which stands for missing at random, which means very non-randomly missing. It's a bad nomenclature. So missingness that's predicted by previous observed variables or other observed variables for the individual is allowed. So it is the best possible missing data handling under the MAR assumption. However, Mplus is also capable of dealing with NM not missing at random, non-ignorable missingness. And in fact, we're about to do a web talk on that topic and a paper on that topic, because there are all kinds of possibilities for latent variables to predict missingness, which is very useful when you have dropout, informative dropout of people over time. Those who have more of a problem dropping out more than others, for instance.
79, slide 79. I was wondering, do we have it?
Slide 79. This
Okay,
Yeah.
I'm getting it. Hold on.
I was wondering why, is there a theoretical reason why we would like to have centering the growth factor at U17?
I think the question is about the centering at U17 here. And could we have slide 78 also, or the growth shape? Or a picture of the curves.
Well,
Maybe
where-
it's that
is
one.
that it?
Graph. Yeah, that's good enough. That's good enough.
Is that good enough? Okay.
Yeah.
Yeah,
So two answers to that. One is that defines the intercept to correspond to age 17. And you, for substantive reason, you may be particularly interested in that peak age here. And you get the mean for each of the three classes here. You can test if this difference in the mean is significant or not. So that's one substantive way of interpreting or answering you. And the more technical is that when you have quadratic growth, it's often useful to center at more or less the average of the time period, because that tends to make the linear and the quadratic slopes more uncorrelated and contributing separate information. If you center at the first time point with quadratic growth, the S and Q factors tend to be very highly correlated, and then that's hard to interpret them. All right, more questions. We have the time.
Slide 55.
Slide 55.
There seemed to be quite a major discrepancy between the outcomes, the transition at time 2, between the conventional LTA and the FMA LTA. I was just wondering, was there a statistical or maybe a theoretical explanation for why they were so different?
So here's the difference between the conventional LTA and that uses latent class analysis measurement models, and the LTA that uses a factor mixture model, introducing a factor as well as the classes. And why do we get a difference? Why does the model fit better?
It would seem strange that a factor would have that much of an impact to change.
I don't know that you should expect this to happen in general. For instance, if you generated, this may be particular to this data set. That is, if you generated data according to this model and fit this model, you may not always see a reduction from 41 to 17. There may be some particular feature of this data set. So I couldn't give an intuitive reason for why this would happen.
On slide 66.
66?
On the last line, you have the scaling factors, and to my understanding, these are used to represent differences in the disturbances across time. I think when you use weighted least square estimation. Does this mean that when we use maximum likelihood, we are in a restricted, in a more restricted model because this is not possible to use anymore?
I'm smiling because I'm getting a déjà vu feeling here. There was I gave a training course at Ann Arbor in 1991, and there was a person who asked very pinpointed questions, and he turned out to be Anders Skråndal, who went to write a big book about structural equation modeling together with Sofia Rabe-Hesketh. We have an expert in the audience here. Okay, so yes. These scaling factors relate to, we have a long story about that, and guess in which topic? We have a long story about that in the weighted least squares context, and the reason we allow this is to allow for different residual variances across time, which is what you find if you do continuous outcome growth modeling. The residual variances are typically different across time. That can be taken into account in the weighted least squares setting. In the maximum likelihood setting, that idea does not seem to have been picked up. So in the maximum likelihood context, we are essentially saying that the residual variances are the same across time, yes. There are possibilities to relax that, but we haven't sort of pushed that to the forefront yet. And in fact, in maximum likelihood, you don't even see any residuals. You don't see residual variances as parameters. You know, like logistic regression doesn't have a residual, much less a residual variance. So it is a technical topic, but I think you're right that that is a sort of a, the maximum likelihood model is a simpler model than what we can accommodate here. All right. More questions?
Well,
this is more a general question. In the example that Linda presented on illness, is it possible to run a generalized estimating equation kind of model in Mplus setup?
So for the schizophrenia example that we have here, is it possible to run two classes?
No, generalized estimating equations.
Oh, generalized. So the question is about GEE, generalized estimating equations. That is not incorporated exactly in Mplus, but close cousin to GEE is the weighted least squares. And actually, on our website, we have a paper that compares the two approaches. Metteans, Dutoit, Spisik paper from 1997?
6?
Well, there's only one Mettean, Dutoit, Spisik paper, but it talks about the relationship between weighted least squares and GEE. So GEE is yet another estimator. It was developed at Hopkins by Scott Zager. And it uses limited information. It's not maximum likelihood. And therefore, it's quite similar to weighted least squares. And they perform very similar to each other. But GEE per se is not, it's sitting inside of the code, but it has not been brought out. Okay, more questions? Are you hungry?
Well then,
one person is not hungry.
Okay.
I'm sorry, folks.
It's about question asked by
the gentleman from Denmark?
Yeah, in 55.
55.
It's
wait, do we have
slide
that?
55. I don't think we
Okay.
have it. This is 66.
Oh, 55. Okay.
Between conventional LTA and FMA LTA,
right.
The increase, could we say that if we control for the factor responsible for the disruptive behavior, we have no equality of change that I people consider disruptive going into in the transition in each group? Others said factors explain that we saw on the conventional ATA that if you are I, you stay I. If you control for the factor, you have equality of chance to be on the two groups. Can we say that?
Could you put up slide 52, please?
52 also? Sure.
If you look at 52, so the original idea was if you're in a high class, but you're low in the high class, you're more likely to transition to the low class than if you're not low in the high class. Do you follow that? And if you're high in the low class, you're more likely to transition to the high class than if you are average or low in the low class, which is saying that the F value, the severity factor value at time 1 influences the class membership at time 2, this relationship. Turned out, though, that I think that's what it's related to what you're saying. It turns out in these data, that path was not significant. The severity values are correlated in these data, but not this one. So I'm not sure. I'm not sure how to interpret this. I haven't really tried to sink into that, but I would recommend, I would encourage you to try to look at it. We have one more question in the front here.
Well, it was about the slide 79.
79.
It's the time points. You center of on 17, but why is 18 is 0.1 and 0.2, 0.3? Why just 1, 2, and 3?
Oh. Okay. The reason, it doesn't really matter whether they're 1 or 0.1, but with a quadratic model, since you're squaring the values for the quadratic, if you keep them too large, then when they're squared, they get too big and it causes estimation problems.
Yeah, it's more of an algorithmic matter.
Right.
Starting values don't end up on an easily handled scale, and things get slowed down maybe. As long as they are equidistant, it doesn't matter if they're 10 or 0.1.
But that's good to bring that up. So you can use 0, 1, 2, 3, or 0, 0.1, 0.2, 0.3, and it really doesn't matter.
You get this exactly the same log likelihood.
Well, here we have a question back here.
Page 84.
In the lower part, you see that there is a significant intercept and non-significant effects for slope and quadratic trend. But in the picture on page 88, you don't see that for class 2. So I was just wondering how to interpret or how to link these coefficients to the picture.
So class 2 on the right is this increasing and decreasing.
Yeah.
Yeah, you see that it increases initially by this positive value, and then you have that decrease. But you're pointing out that they are not significant here.
Yes.
So you could not, in this case, reject that is actually a flat line sitting somewhere up here.
Okay.
Yeah, and that's a correct statement. You know, it may have a higher level than the normative class, but you don't have a significant up and down behavior, so you could not reject. So what you can do in this situation is you can use model test, which gives you a walled chi-square test, that these two coefficients jointly are 0. You know, when you talk about two things, it's not sufficient to say that each one of them is insignificant, because you also have their correlation between them. So you really should do a test of them jointly being 0, and that may be rejected. So the point estimates suggest this quadratic shape, but the significance of each is not there. That's how you think about it. Now, that's okay, you know. We can present insignificant results and just say this is not significant. Maybe it's because it is 0, or maybe it's because our sample is too small, but let's just report the results.
But in class 3, you find a significant quadratic term, but it's not depicted in the picture.
So if you go to slide 85, Linda, let me see class 3.
On that screen?
Yeah. Or maybe 86.
Right. And so in that one,
the quadratic is significant here. So it's a significant quadratic downturn from 17. Yeah. But you don't have a significance for this S either. But again, you could do that model test of them jointly being 0. Now this is only 400 individuals and polygamous data, so you can ask how much power do you have to reject that they are 0, and that can be answered by a Monte Carlo simulation study. Okay, more questions? If not, then how about if we gather back at 1:30 and we wish you a nice lunch.
Thank you.